Okay, so we are moving into the next part of this session. So welcome up Cheol Jeong, who is an associate professor at the Technical University of Denmark, and you will talk about problems of absorption coefficient as input data for room acoustic simulations.
Yes, thank you, Emma. And thanks for inviting me in this nice EIAS conference or seminar. I'm going to talk about sound absorption coefficient. I knew that the audience here is a mixture of architects or acousticians, and so I kind of chose this non-technical or less technical topic. So I hope this is enjoyable actually for you guys. I'm Cheol Jeong. I'm from Technical University of Denmark. And yes. So as you know, the absorption coefficient is defined as the power ratio of the absorbed to the instant. And this figure is very nice actually, nicely illustrating how the absorption coefficient is calculated or measured. So the original definition is basically 2 sound power absorbed divided by the instant sound power. But in reality, we actually use this kind of equation. So we are adding the transmitted part of the energy into the numerator like this. So in reality, we are using different definition than the kind of original definition of the sound absorption coefficient. So this is the problem number 1, in my opinion. Many manufacturers, they used sound absorption coefficient, but they used the practical absorption coefficient. And I'm not sure actually how many of you are really understanding what the practical absorption coefficient. Can you raise your hand if you really know how this is calculated? Yeah, it's quite many. Yeah, so they use the practical absorption coefficient like this. It's 0.1 at this frequency, and so go on. And the weighted absorption coefficient is 0.7. So this is a single value weighting. So there's a specific way to get this weighted absorption coefficient, and in the end, it's absorption class C. And it's also written that it is strongly recommended to use this single number rating in combination with the practical absorption coefficient. I don't know why this is strongly recommended to use the single number rating. And Emma, in one of her papers, she also used the practical absorption coefficient. And as you know, practical absorption coefficient is kind of truncated and rounded sound absorption coefficient. So we measure the absorption coefficient in reverberation chambers, and anything higher than 1 is just truncated. So I think that's a problematic. Then we also use absorption classes A, B, C, D, E. And then we tend to say absorption A or class A is better than B, B is better than C. And also a little confusing part is that with the same sound absorber, the absorption class can be A or B or C or D or E. So that's a little confusing. When I look up Ecophone product, then it's a class A absorber, but it depends on the mounting condition. So if you mount it correctly, it will be a absorption class A, but if you don't use the correct mounting condition, it can be D, absorption class D. So that is kind of confusing or kind of miscommunication between the manufacturers and the end users. I hope Ecophone is not hating me after this presentation. So we have 2 different curves here, the blue one and the red one. They are real products, and this is a practical absorption coefficient. Which one looks better? How many of you think blue one is better than red? No one? Okay. And everybody believe red is better than blue? How many of you believe red is better? Okay. That's totally opposite to my expectation. Anyway, when we are making classification, then the blue line becomes class D, and the weighted absorption coefficient is 0.45 because it's lacking low frequency absorption at 250 Hz. And the red one is class C, so it has the weighted absorption coefficient of 0.7. I tend to disagree because I mean this blue one can be quite nice actually at 1 kilohertz and 2 kilohertz. It has much higher or somewhat higher absorption coefficient. That's a very important frequency range. So I kind of disagreed, but everybody unanimously agreed that the red is better than blue. My fault. Yes, and this is one question. If I ask you to calculate the sound absorption coefficient of 10 centimeter observer backed by 10 centimeter air cavity, and I can give you a lot of more detailed information like flow resistivity, porosity, and everything. I believe I will get at least 100 different answers from you. That's basically because there are so many definitions of the sound absorption coefficient. So if if someone asked me this question, I could actually calculate the normal instance absorption coefficient. The sound is coming from the normal direction, 45-degree angle and 80-degree instance angle. These are quite different actually. And if I use the local reaction assumption or extended reaction assumption, these curves are slightly different, but not very much, but anyway, slightly different. So these three, normal instance, random instance, and the local reacting condition, they are based on infinite panel. So we base that this is really big, large panel. So they are based on the infinite panel theory. In reality, according to ISO 354, we measure 10 or 10 to the 12 square meter sample. So depending on the size of the sample, the sound absorption coefficient changes. So this is one thing. Of course, I mean, I've never seen any infinite panels in reality. Of course, then the ecophone is really rich, then they will host this kind of event every year, not every 4 years. But I mean, we use finite samples. And depending on the size of the sample, the absorption coefficient changes. And this is kind of calculated absorption coefficient. If you're doing the measurement of this, the same observer, we have very different values. So depending on which chamber you are going to measure, the sound absorption coefficient changes a lot. We have very mysteriously having like 1.3 as the absorption coefficient. That means this observer is 100% or 130% absorbing material. That's nice, but that's not real. So that's the ISO standard measurement, and this is the kind of theoretical calculation of the ISO standard. So I think one of the main problem is this sound absorption coefficient is overly confusing. There are so many definitions like normal instance absorption coefficient, random instance absorption coefficient, and statistical absorption coefficient, and Sabine absorption coefficient, and basically practical absorption coefficient, weighted absorption, and absorption class. That's based on the Sabine absorption coefficient, which is very uncertain. Well, I will talk about that a little later. Yeah, so there are so many definitions, and I don't know if someone is talking about absorption coefficient, which absorption he or she is talking about. So that's the problem. There are two main issues when we are using sound absorption coefficient. We use the sound absorption coefficient data improperly. So we sometimes use the random instance absorption coefficient for anisotropic condition. More problematically, we use the normal instance absorption coefficient for random instance situation. So I saw so many papers, so many reports saying that I use the normal instance absorption coefficient in this room simulation, which means that the sound is only coming from this direction. It's not the case. It's hard to believe that. And we use averaging over the angles, instance angles, and the frequency. That makes the absorption coefficient data quite vague or not properly. And we also use wrong assumptions like infinite panel, plane wave instance, and no phase shift in in the calculation or in some calculations. So this is the problem in when we are calculating the sound absorption coefficient. When it comes to the measurement, the problem is actually bigger. We have very different definitions of many absorption coefficients, and we have very simplified measurement procedure according to the ISO standard. We are using two sets of reverberation time, and we convert into the sound absorption coefficient. All the reverberation chambers diffusivity is different in many different ways. So we cannot really sure that this reverberation, all the reverberation chambers are in a good quality, I would say. And some people actually use not correct source and receiver positions in the measurement. And the main problem in the ISO 354 is that the sound absorption coefficient is changing with the sample size. So if you measure 10 square meters and 20 square meters, then it's totally different. I tend to say this part is little more problematic than the inappropriateness of the sound absorption data. I think this is well known in the community, the ISO 354. The sound absorption coefficient is depending on the sample size. So the smaller the size, the higher the absorption coefficient. And of course, as a manufacturer, I think it's tempting to use 10 square meters instead of 12 square meters. And it can exceed unity. So it can be higher than 1. So 100%, more than 100% absorption. So it's not the most appropriate input data for these simulations. And the main part is actually the interchamber reproducibility is really poor. And this was done in 2010 by Verkaman round robin test. And you can see different chambers are yielding different numbers. So especially if you look at the low frequency 100 Hertz, one chamber you get 0.1. If you are very lucky in this chamber, the sound absorption coefficient is 0.6. And nobody knows the truth actually. Yes, so there are so many problems in this. I think one of the also, it's not a problem, but the absorption classes are most useful for the manufacturers like Ecofon. So they sell it and saying that this is a class A absorber, class B absorber. That's easy to say, but as a user or as a customer, we want to know how much our room will be improved by using this absorber. We don't care if it's A or B. So very famous quote, people don't want to buy a 1/4-inch drill, they want a 1/4-inch hole. The same, people don't want to buy class A absorber, they just want a sound absorber that can fix their problem in a proper way. It doesn't over-dampen the sound field, of course. I criticize the ISO standard very much, so do advanced measurement help? I'm not very convinced, at least. I mean, this is a paper by our German colleague in Aachen. They actually measured the surface, and this is one of the benchmark database, and they used the PU proof, so particle velocity and sensor, very advanced technique. When they are using in situ measured data, the deviation of the reverberation time from the measurement is 80%, so almost twice bigger or half the real measurement. When they are using some known database, so like there are some database of the sound absorption coefficient, this is actually better than just in situ measurement. So blindly doing some in situ measurement using those data, it doesn't help the problem. Also, we have used a lot of microphone arrays. This is 128 microphone made by B&K, super expensive, you could expect. And this is 64-channel microphone array. And we actually realized that the sound, the surface impedance around 60 degree is much less accurate than the smaller angles like 0 degree. So we cannot really capture the whole dynamics of the sound field using those small sensors. So my suggestion is to convert the known database or trustworthy database to the phase included boundary condition. So phase included boundary condition means the surface impedance or reflection coefficient and basic material property like airflow resistivity. And I did some research, but I'm not going to all the details. I just want to say one good thing about Ecophone. Ecophone is actually willing to provide all these basic material data, like flow resistivity, so that I could calculate the angle-dependent complex value surface impedance or the reflection coefficient. It's really nice. I know some other companies, competitors of Ecophone, they don't want to share anything. When I ask them, can you provide your flow resistivity? Then they say, you could actually measure it in your lab. You do it. I will not say anything to you. So that's, I think, more data, more basic material data is really nice to complement the sound absorption coefficient. Okay, I want to make a smooth transition to the next talk. So Finno will talk about these wave-based simulations, and we actually need phase-included input data for the wave-based simulations. And one of the previous collaboration with Ecophone, Giyad Mabia's PhD project, we actually used the image source method, and we compared the simulation of image source method to the FEM simulation. So FEM is known to be the correct or more correct sound pressure estimation. We are using the same method, image source method, but in one case we have a really good match. In another case, or in the other case, we have really, not very nice agreement at low frequency. So when we are using the angle-dependent and complex-valued pressure reflection coefficient, we have a really good match. When we are using the random instance absorption coefficient, the low frequency accuracy is really bad. So we have to use the phase-included input data instead of the energy input data. Okay, I will just quickly say this is one case having this kind of surface or ceiling, and when we target some kind of parameters, we want to make the clarity value higher than 7 dB or 5 decibel, then I hope the software will automatically search in the database and then suggest this, instead of saying that you have to use absorption class A or B. So this is the right way. We have to use this kind of calculation software to show that this is the right solution. Okay, my conclusion is reflection is too complicated to be quantified by a single number rating. So I don't trust single number rating like weighted absorption coefficient and the class A, B, C, D, E. No, that doesn't help so much. The sound absorption coefficient is energy-based. At least we have to know the limitation of the sound absorption coefficient. It's energy-based. It's angle averaged, which is not nice, and also frequency averaged, and also sometimes brutally truncated. So I got quite disappointed to use all this practical absorption coefficient in my research. And of course, the best boundary condition is the phase-included boundary condition, also angle-dependent boundary condition, either in the form of surface impedance or the pressure reflection coefficient. And of course, you can get the best outcome when you use the pressure-based simulations. Thank you very much.